Hi everyone, I would like to welcome all of you to Frontline Systems webinar on an overview of optimization applications in Excel using our advanced products. My name is Dr. Sima Malika. I'm Consulting Lead and Modeling Specialist at Frontline Solvers. During this presentation, if you have any questions or comments, please type them into the chat box to be answered at the end as time allows. I strive to remain within the promised time frame, yet to thoroughly cover all the material. Sometimes it takes a few minutes longer. I very much appreciate your cooperation. As we all know, the optimization applications are widely used across many industries and functional areas: energy and utilities, chemical, manufacturing, transportation, financial services, and some of functional areas: staff planning, scheduling, routing, blending, capacity planning, and so on. We would like you to know that many of our customers have found optimal solutions for their industrial large-scale problems worth millions in savings, as building a model can give you insights and a money-saving optimal solution. Today, we explore how optimization can benefit you in solving your business problems and how easy it is to use our tools to solve them. Together, we will review typical applications in transportation, inventory management, financial services, scheduling staff, and one example of automating optimization using VBA. Maybe you wonder what solvers are good for. So let's start talking about the decision-making process and using optimization to solve a problem. It is always best and most powerful to efficiently allocate scarce resources arising in your business. It can be your money, equipment, staff time, transportation fleet, or raw materials inventory. All of these are resources and they are allocated for some purpose. Deciding on which products to ship from factories to warehouses along each route is an allocation of products to routes. Portfolio optimization is allocating money to stocks in a portfolio, and scheduling is really a matter of allocating people to time slots or scheduling the availability of hospital operating rooms. Solvers or optimizers are software tools that help you determine the best way to allocate those resources. You might be wondering what you need to do to use a solver or how to define your optimization model. Let's drill down on this further. There are three main steps. They are determining your decision variables, objective function, and constraints. Each optimization problem involves one or more decisions that must be made in order to solve the problem. The decision variables are typically numbers reflecting how much of some scarce resource is being allocated to some use or purpose, and that is normally under your control. These decisions need to be made in the best possible way while simultaneously satisfying a number of logical conditions or constraints. Constraints reflect the physical situations, and there are various types of them. Some of the constraints represent limits on available resources such as inventory or money. There are constraints that reflect the physical situation. One of them is non-negativity on variables. You can't produce a negative number of products. You cannot assign a negative number of people to tasks. Some constraints are determined by policies that you or your organization may set. For example, in a portfolio optimization, you might have a limit on the maximum percentage of funds to be invested in any one stock or one industry group. Then you might have balance constraints. For example, the beginning inventory of this cycle equals the ending inventory of last cycle. Another common element in each optimization problem is the existence of some goal or objective that the decision maker considers when deciding which course of action is best. You can determine objective function by asking what measures are we trying to optimize. The best or optimal solution might mean maximizing your profits, minimizing costs, or achieving the best possible quality. Now, it is time to dive in and see how we can solve a problem in practice. We are going to look at an advanced example. The goal here is simply for you to see different components of an optimization problem, the decision variables, objective function, or various types of constraints that one needs to consider in a typical real-world application. So please don't concern yourself with details. I will point you to where you can find the examples that we are going to review today by end of the webinar. Transportation and logistic operations of your company can be a competitive differentiator. Let's find out how optimization can be used to optimize a transportation operation. This company has 3 different goods that have to be shipped from 2 factories to 4 warehouses, and from those warehouses to the 5 customers, or directly from factories to customers with minimum cost. You can see here is a diagram of the system with nodes for factories, warehouses, and customers. Now, we need to show the supply-demand pairs displaying feasible routes for the shipment plan. These gold color arrows show the potential flows from factories to warehouses and customers, and these green ones show the potential flow from warehouses to customers. Each arrow here represents a different route. What needs to be decided is how much product to send on each route, meaning it is under your control. Let's take a look at the Excel workbook. I'm going to increase the size. This is the full analytics solver platform ribbon, which includes optimization, simulation, and also data mining through Excel Miner platform. Today, we are going to focus on a subset of Analytics Solver Platform, or ASP, which is called Premium Solver Platform. So, we can change the product. When you are using a free trial of our software, you can also do this. Let me show you how you can do this. Click on Help. The first option is Change Product. Here, instead of Analytics Solver Platform, let's choose Premium Solver Platform. And now click OK. So we just now have the access to optimization components. Let's skim through the Premium Solver Platform ribbon together. As you can see, clicking on this model tab displays or hides the task pane. Here is the model drop-down menu, and it has additional options for multidimensional modeling that are beyond the scope here, but examples are available. Optimization model tab allows you to set up your optimization models. This includes all the components, your decision variables, your constraints, and your objective function. And we are going to practice to use them together. Parameter tab provides the options to run multiple parameterized optimizations. Again, we are going to practice that today as well. Solve Action tab allows you to solve your optimization models. In the Analysis tab, you can have access to reports and different charts and analyze your results. Tools tab enables you to create decision to examine your optimization results. And then if I click on Publish button, this facility allows you to publish your models for use and distribution on the web. This includes Excel Online and Google Sheets. Get data allows you to summarize from big data. You can bring in your input parameter data that you would use to drive an optimization model. For example, if you have millions and millions of sales orders in a large database across different hard disks, you are not going to use every single order in your optimization model. With this facility, you can get a sum or average based on region or gender. Next, let's explore the Help tab. Here you can display online help, use live chat, control guided mode, which we'll discuss in more detail today, open examples, user guides, and reference guides, and check your license status and more. So now let's go on to the task pane. Model tab allows you to view the model in outline form, see the results of model diagnosis, and optionally edit your model elements in place. Next is Platform tab. Here you can view or change the platform options such as the number of optimizations to run or the default bounds on your decision or variables. You have the Engine tab. Here you can select a solver engine and set its options. And then finally we have the Output tab, allowing you to view a log of solution messages or a chart of the objective value. Now back to our example. There are two goals that need to be carefully addressed in this problem: the total costs of shipping and the service. We want to provide the service with minimum cost and ensure that each customer demand is completely satisfied. As you can see in this Excel workbook, the cost of shipping from factories to warehouses, factories to customers directly, and from warehouses to customers are recorded in these cells. These are inputs to the problem that are not under our control. For example, these shipping costs are quoted to us by our outside shipping company, for example. Yeah. What is under our control are decisions about how much to ship along each route at these different locations. So we need to reserve cells for variables representing quantity shipped between factories, warehouses, and customers. This is how we define decision variables, and as you can see on the right side, in the Model tab, 3 sets or 3 blocks of variables which have name ranges are defined. Let's quickly look at what a name range is. So let me open a blank workbook just to prevent any confusion. So I can select cell A1 through C1 as my decision variables by clicking on this button, and then you can see in the task pane A1 through C1. This range of cells is added under variables under our optimization components in the Model tab. Now I'm going to select range A2 through C2 and give them a name such as, I don't know, VB. Now if I select this range and define them as our decision variables, you can see that VB is added under variables in the task pane. So our products recognize these name ranges and they are helpful to manage your large scale models. So let's go back to our transportation model with a lot of name ranges. What measure are we trying to optimize? Each route of flow incurs a cost. So our objective function is minimization of total cost of shipment along all the routes. You can see we call it total cost, and this is defined in cell C91 highlighted. So let's take a look at the formula. This is C91. You can see that this formula is represented by a sum product function, different components of three different sum product functions. Let's look at the first one. To calculate total cost of shipping from factories to warehouses, since the cost coefficient for these routes are defined in cells C10 through F15, we need to multiply these by total amount of the product that will be determined to be shipped. Our decision variables for which we have reserved cells C41 through F46. And similarly, we need to add other costs. This one and this one. Now on to constraints. What restrictions limit our choice of decision variables? The capacity of each warehouse, supplies available from each factory, and the demand from each customer need to be considered. So here are the warehouse capacity constraints. We want to make sure what we ship into the warehouses doesn't exceed the capacity of those warehouses. We cannot overload warehouses as each one has a physical capacity that are recorded here in these cells with just, again, it's a name range, warehouse capacity, these are constants input to the model, and then here we are calculating total that is shipped to warehouses. We have a certain supply available at each factory provided in cells H63 through H68. The total flow out of factory 1 for each product type must be smaller than or equal to the factory supply, which is 90,000 here. And then this is the same for other products and the other factory. Then we need to ensure that each customer product demand is satisfied. And then here are these constraints. Total customers must be greater than or equal to the demand. Warehouses are temporary holding points, therefore flow out from one warehouse is equal to its flow in. And then you can see we have these balance constraints with the equality form, so we have different forms for constraints. We are going to discuss that. And total to warehouses equals to total from warehouses. Okay, now let's go ahead and solve the model by clicking the Optimize button on the ribbon. This time we are going to step our way through guided mode and see what it can tell us. This feature is a guide offering help for you in each step of your modeling efforts with information to help prevent common errors. Let's click Continue. Two things happen here. First, Solver has analyzed all the formulas in this model and determined the structure of our model automatically. This model is LP convex. LP stands for linear programming. Because the right solver engine wasn't selected, it is letting us know and giving us other choices. So by mistake, I chose standard LSTRG nonlinear, which is a good engine for a nonlinear type problem, but it's telling me that I should choose the LP, standard LP engine. Okay, now I'm going to select this, the engine that is offered, and click on Next Step. Now, guided mode tells us that Solver found a solution, all constraints and optimality conditions are satisfied. Let's click OK, and now we are back where we were, without the guided mode. Here is the solution. We achieved what we wanted here, which was to determine how best to ship products between the factories and warehouses, factories and customers directly, and warehouse and customers. So to minimize our shipping cost, which is $519,700. After you have used this guided mode for a while and you're solving over and over, you might want to get rid of the dialogues that you have to click through every time. To make this change, click on Help, Operating Mode. You can see that there are different options. Instead of going to Expert Mode that eliminates the help, you have another choice, Auto Help Mode, which will only bring up the dialogues when there is a problem. We just looked at how optimization can help us with a typical transportation problem. Next, let's look at an inventory management example. Then we can define an optimization model from scratch. Let me increase the size. This problem is about a warehouse that sells 4 products with a different demand for each product. Each product has a different holding cost and requires a certain amount of space. We have a limited storage capacity. So, what is the best ordering policy for a warehouse to minimize costs while meeting demands? There is an analytical solution for this problem, which is known as the economic order quantity, or EOQ. Unfortunately, this formula doesn't always work in the real world. Demand usually fluctuates, ordering time is variable, and other factors arise to further complicate the problem. In this model, we have one such factor, a limited storage space. Let's review the optimization model components together. The variables are the amounts to order each month for each product. You can see they are defined as quantities. Let's double-click the cells B13 through 16, this whole block. And then our constraint is the storage capacity constraint. Storage space use should be less than or equal to the available space. And then our objective is to minimize total costs. If the storage limit wasn't present, the solution to the problem could be calculated by the EOQ formula. However, given the storage limits, the solution will be less than EOQ. Let's take a look at the objective, which is calculated by adding the individual costs for each product. Let's look at one of the formulas, for example, for the first product. You can see this formula is calculated as holding cost times average inventory level plus the cost to place an order times average number of orders. Having the variable as the denominator changes this model from a linear structure to a nonlinear one. Let's click on Solve and see the guided mode verifies that, if the guided mode would verify that. So let's click on Optimize, click on Continue. As you can see, guided mode is diagnosing this model as an NLP, which is nonlinear programming. Let's click on Next Step, and then Solver found the solution, and here are the results, which are the amounts to order each month, minimizing cost, meeting demand, and without exceeding storage space. Now on to our example in a financial services application, allocating money to stocks. An investor wants to target a specific rate of return for his portfolio while minimizing risk. This is a portfolio optimization application. So the goal is to find the best combination of stocks that minimizes risk for a given return. Let me open the Excel workbook. If you take a look at the model tab, you can see under optimization, there's no decisions or constraints or objectives. So we are going to define this optimization model together. And then you can see that the returns, variance and covariance between all stocks are known, and I've organized this data and created some formulas that we need on the spreadsheet. So the decision variables are the percentage allocations of the funds that we can invest in each of 5 stocks. So we need to have 5 cells for representing each of them. I plan to use cell C14 through G14 to hold the percentage allocations of the funds or the decision variables. And then I've used the name range allocations for this block. Now we have to let solver know that. So use the mouse to select this range for decision variables on the worksheet. Then click on decisions and normal on the ribbon to define C14 through G14 or the block allocations as normal decision variables. And you can see in the task pane model tab, the allocations are added. So this is the way for you to verify that if you have done it correctly by checking the model tab on the task pane under optimization variables. To define the objective of our problem, first we need to create a formula on the worksheet to calculate the measure that we need to optimize. Here, in this problem, the measure is portfolio variance. Then, we need to tell solver whether we want to minimize or maximize our measure and where that formula is. So, in cell C18, I have defined a quadratic function to calculate the portfolio variance by this custom quad product function. Now, you can use the mouse to select C18 on the worksheet, then click on Objective, and Min to define C18 as our objective to be minimized. Again, if I go on this cell C18, you can see I defined it as portfolio variance. To verify this, that we have done this correctly, you can check the Model tab, this time under Optimization, the objective, which is portfolio variance, and it is going to be minimized. For this problem, we have 2 constraints. We want to make sure the total portfolio equals 100% and that its return is at least 9.5%. For the first constraint, we need to calculate the total portfolio with a sum function over the allocations. Then we need to tell solver that the sum of allocations of funds to stocks equals 100% or 1. I have used cell H14 to represent the formula of this constraint. Here, sum of all allocations, sum of C14 through G14. Now, use the mouse to select a cell on the worksheet, then click on Constraints, and then the first one, Constraints. Let's choose the equal sign to define H14 as the left-hand side. Again, the name range was total portfolio for this sum. In this Add Constraint dialog, now we can enter 100% or 1 for the right-hand side. Let's enter 1. Let's click OK. Now look at the task pane. Model tab, you can see that this constraint is added, which has an equality form. Second is total portfolio return, which must be greater than 9.5%. We need to set up one cell in the spreadsheet to represent the formula of this constraint. Here I've used cell C20. Name is portfolio return. Let's take a look at the formula. It is a sum product of allocations and stock returns. Now use the mouse to select the cell on the worksheet, then click on the constraints. First one, constraint, and then choose greater than or equal to define C20 or portfolio return as the left-hand side. In this add constraint dialog, now we can enter 9.5% as the right-hand side, then click OK. You can check the Model tab, task pane to verify the constraint is defined correctly. By doing this, we have defined our business problem in the optimization language for Solver. Now we can hit the Solve button and get the results. Let's click on Optimize, and continue. You can see this model is diagnosed with a quadratic programming structure. Now let's click on Next Step and we get the optimal solution. This is the allocations of funds to different stocks resulting in the minimum risk or minimum variance portfolio that equals 100% and achieves a 9.5% return. This is often called an efficient portfolio. You may have heard of the efficient frontier. Using Premium Solver, we can construct that efficient frontier rather easily. Here I will show you how. So far in our example, we have used the solver and found the optimal portfolio with minimum variance for a given target rate of return of 9.5%. Let's generalize that. We can utilize parametric optimization to find the efficient frontier that is the optimal solution for several levels of portfolio return. To do this, let's choose an empty cell. For example, D20, and I'm going to change its color so we know where it is. Okay. Then select it, then click on Premium Solver Platform, Parameters, Optimization. To insert a parameter, this dialog box will open. We are going to define a parametric return rate. And we would like to see the optimal solution for different return values between 8 and 14%, as one of our stocks returns 14%. So let's input 8% for the lower level and 14% for the upper level. Let's click OK. You can see that D20 now includes this psi up prime with 8% and 14%. You can also click on Model tab, and under Parameters you can see that D20 is added. Markowitz is the name of this worksheet. Now we have to modify our constraint right-hand side to point to our parametric return rate instead of the constant value of 9.5% in the right-hand side. So let's double-click on this constraint in the Model tab. Click on this button and point to D20. So you can see the right-hand side is now pointing to our parametric return rate. Let's click OK. Double check that this constraint is correctly modified. Now we need to tell Solver that we need to run, for example, 10 optimizations so that Solver finds the solution for different levels between 8 and 14%. So let's do that. Do that through clicking on Task Pane Platform tab and set the number of optimizations, which is the first option, to 10. I am going to clear the output report so you can see what's going to happen here. Now let's click on Optimize. I'm going to skip guidance, and here are the results. You can see 10 optimizations just finished. The worksheet will initially display values for the last optimization. You can see the return value is 14%. But we can display any of the optimization results by changing the selection in optimization number on the ribbon. For example, let's check the second optimization. Here are the results. You can see the return rate for that specific optimization model. Our total portfolio is always 100%, and you can see the value of our objective function. Now, let's click on Charts, Multiple Optimizations, Monitored Cells. Let's select the objective cell portfolio variance and click OK. This is the efficient frontier plot. Let's click on this button to the right side, open the right pane. Let's open the chart options through this drop-down menu. Down below here, for X coordinate, we have two options, either the optimization number or optimization index or the value of our parametric return rate for that specific optimization run. You can see it is now based on optimization index. We had 10 optimizations. We can change it to opt-param at the parametric return rate. So you can see the return threshold for each of these optimizations. Okay, let me close this. Let's go back to our slides for a recap on what we practiced: modeling and solving problems in Excel spreadsheets. First, you need to determine your decision variables and reserve required cells to hold the value of each variable. Then, pick a cell to represent the objective function and enter a formula that calculates the objective function value in that cell. Then pick other cells and use them to enter the formulas that calculate the left-hand sides of the constraints. The constraint right-hand side can be entered as numbers in other cells or entered directly in the solver at constraint dialog as we practice. And one quick note, it is best practice to use constants for constrained right-hand sides. So if you have formulas that depend on your decision variables in the right-hand side in the B1, just move everything to the left-hand side and try to keep constants on the right-hand side. Now, let's look at some scheduling examples. This example is about allocating staff. An amusement park needs a certain number of employees each day of the week. Every employee must be on a schedule that gives him or her 2 consecutive days off. How many employees should the park hire, and what schedule should they be on to minimize total payroll cost? Let's open the workbook. So, for employees working 5 consecutive days off with 2 days off, we are looking to find the schedule which meets demands from attendance levels while minimizing payroll costs. We have 7 possible schedules, A through G, with the days off represented here. Decision variables reflect the number of people hired for each of the 7 possible schedules. And then we have the total demand recorded here. So we need to tell solver that the solution need to be integer values because we're talking about the number of people hired. So we need whole numbers such as 2, 3, or 5 people. To do this, you need to select your variables. So these are our decision variables. Let's double check. These are this block of variables, D7 through 13. Let's select these decision variables and let's tell solver that these need to be integer values, again, whole numbers, 2 people, 3 people, 5 people, 7 people. So let's click on constraints, variable type or bound, then choose integer. You can see that now these variables are defined as integers in the model tab of task manager. We have 2 set of them. Let's right click and just click on delete. And then here our constraint is total demand that need to be satisfied. Employee per day should be greater than our required employee per day or our demand. Also, we need to tell solver that the variables need to take positive values. There are 2 ways to do this. You can select the variables and then click on constraints, variable type bounds, and then choose greater than or equal to and then put 0. This is one way to define decision variables as positive values, and you can see it appears under bounds for your decision variables. There is another way to do that because this is such a common occurrence. We have a shortcut for it. Click on Platform tab on the task pane, and there is, the Engine tab, and there is Assume Non-Negative. Here an option, assume non-negative, you can set it to true or false, and that just does the same thing that we just did to set all the decision variables as true. Which we can see is already set for this problem. So let's go back to Model tab and just delete this constraint. Let's solve this problem. Click on Optimize. I'm going to skip guidance to get the results quickly, and here are the number of required people for each schedule to minimize our payroll costs. Now, the next workbook is another version of this problem. The park has hired the required employees. It now needs to decide which employee goes on which schedule. To do this in a fair way, each employee has given a list with his or her preferences. You can see the list here. So these are the schedules A through G, and these are the employees that we hired, 25 employees. These are the preferences listed from 7 to 1, which 7 means the most desired schedule and a 1 means the least desired. How should the park divide the schedules among the employees to maximize the preferences? We have to define 7 decision variables for each of 7 schedules per employee. Then decide to allocate only one of their schedules to each employee. Whether to allocate a schedule to an employee is a yes-no type question, or the yes-no type decision. And we have an easy way to do this in optimization modeling. We can define the variables as binary, meaning the variables can take only 0 or 1 values. This whole block is our decision variable. So let me show you in the Model tab. If I click on decision variables, you can see this whole block is called schedule and it's highlighted. So if one of these variables here in this cell or 24 takes value of 1, it means that employee number 1 is assigned to schedule F. To define cells as binary variables, first define them as variables, then select all of them, and then click on Constraints, Variable Type Bounds, and then we have binary. And you can see that this was already added, so I'm going to just delete one of them. Now, we need to tell the solver that each employee can be allocated to only one schedule. So we need to define a sum function over the variables related to each employee. Here, this block of 7 variables. And then define a constraint and make all of these sums for each of the employees to equal to 1. So I have this sum for employee 1, this sum for employee 2, all the way to this separate sum for employee 25, and then I have selected this whole block. This is an easy way you can define constraints. Click on constraints and select equality, enter 1, and then click OK. Now that is how you can add this kind of constraints. So let's delete that one of them because it's already here. So this was the constraint. Schedule per employee must be equal to 1. Then the employee schedule have to be equal to the required employees. So we need to sum all the variables that are under one schedule. So all the variables under schedule A, for example. Then here's the sum. So we have sum of all the employees, total employees that are assigned to schedule A. So this way we calculate total number of employees within that schedule. Then we can define this constraint. Employee schedule must be equal to the employee required, total number of demand for each schedule. So again, this is another sum for schedule, second schedule. Then we have it all the way to schedule G. Then you select this block and make it equal to your demand. The objective is to optimize employee preferences, and in this case that means maximizing the sum of the preferences over all the employees. This sum is defined in the worksheet as total preferences. So you can see it's in U50. Let's check one of the components. So let's check on U50. You can see it's the sum of all preferences for employee 1 through 25. Let's check number 1. We have used this sum product function to multiply the array of variables by the array of input expressed preferences. So you can see for employee 1, if she or he is allocated to schedule F, we have one variable under F that takes the value of 1 and all others are 0. Recall that only one schedule will be assigned to each employee. Since the expressed preference for schedule F is 7, this sum product for employee 1 returns 7. And this value contributes to our objective. And this is the same for the second one. Let me enter 1 here, and you can see this contributes a 1 to objective. Why? Because the preference of employee 2 for a schedule E is only 1, like really not preferred at all. Okay, we are ready. Let's click on Optimize. Let's skip the guidance, and here are the results. Then we can see the assignment of employees to the schedules, and we can see that only one employee is assigned to each schedule. This model will solve the problem after finding the optimal solution of scheduling 1, the previous problem. It is also possible to find both solutions automatically. You can write a VBA macro to do this. It is actually a good time to talk about automating your models. This allows you to run your predefined solver models and control the guided mode. Control the solver and all the options such as guided mode. You can automatically update data run the model and retrieve the results, and also create an application to distribute to your end users. You can automate your models and control solver engines using VBA Object-Oriented API. We're going to look at the refinery example. The VBA code for this model shows some of the many ways you can use the Object-Oriented API, such as how to call a solver and how to retrieve sensitivity information from VBA. So this is about an oil refinery that purchases 2 crude oils. These crude oils are put through 4 processes: distillation, reforming, cracking, and blending, to produce petrols and fuels, which are then sold. The goal is to plan the operation of the refinery to maximize total profit. As you can see that the model components, including decision variables, constraints, and objectives, are defined. So now we're going to review the code together to see how to call the solver to this predefined to solve this predefined optimization, and how to retrieve the sensitivity information. So let's click on Developer tab, Visual Basic. Here's the code. Within problem as new problem, you can create an instance of a problem. I want to skip these details. This example is available to do there for later. The next very important one, so here we pick an engine, solver engine, then we set a parameter for that engine. But you could just directly have dim prob as new problem and then jump to prop.solver that optimize, that runs the optimization. In the next line, we are going to put a message box. We will see as we run it, and then down below there is another for loop. Within that for loop there is another message box where retrieving reduced cost, shadow prices, and final variable values. And then at the bottom we have prop.solver report, and we are asking for an answer report, and you are going to see that happen when we run this. Now let's close this and then click on Run Model Macro button. You can get the optimization status, meaning found the optimal solution. Then we get the final variable values. And if I click through this quickly, you can see the rest of decision variable values. Then you get the reduced cost as requested in those for loops and shadow prices. And finally, you can see an answer report is generated for us. Now a quick review of our product line. You can access our optimization software within Analytic Solver Platform or Risk Solver Platform products, or get it as a standalone program such as Premium Solver Platform or Premium Solver Pro. Everything that we saw today can be done using Premium Solver Pro or more advanced products subject to your model size. The Solver Upgrade products have very nice usability features with limits related to problem size, structures, and solver engines. The platform products allow you to add 8 different large-scale plugin solver engines that you can use to extend the power of these products. These make it practical to solve very large problems, essentially only limited by memory. But you can do much more with our products. We offer a complete solution for any type of conventional and stochastic optimization problems, simulation and risk analysis, decision trees, and forecasting and data mining. You can find optimal solutions for models with uncertainty using chance constraints, recourse decision variables, and robust optimization and stochastic programming methods. This wide-ranging product line empowers you to perform analytics on the web and desktop spreadsheets, also web, server, and desktop applications in any scale. As we mentioned earlier, many of our customers have found optimal solutions for their industrial problems worth millions in savings. We saw today how building a model can give you insights as well as a money-saving optimal solution. Frontline Solver offers powerful tools to help you get a better solution by automatically diagnosing your model structure, fixing problems for you, selecting the solver engine, and providing updated information at each step. For instance, one of these features, the guided mode, helps us choose the right engine. You might be asking, what is the next best step to begin? Please register at our website for free. This allows you to access our downloadable user guides, more than 40 example models like the ones we have been showing here today. Furthermore, it allows you to download a free trial at any time whenever you're ready. Try this yourself after installation. Go to example models. I'm going to show you in a second. During this trial period, you have full technical support. You can ask questions. Just give us a call. This is a special number for this webinar attendees. Use live chat or send us emails. So let me show you how you can access examples before going to your questions. Click on, after installing any of our products, click on Help and then Examples. Here you can access all the optimization examples, simulation, decision-based data mining, and so on. And to access the examples that I showed you today, just click on Optimization, line 19, and then, for example, for the transportation problem, click on Logistic example, and it is Transport 3. I really enjoyed presenting this webinar and trust that it was helpful to you. Let me share my email with you, which is consulting@solver.com. I'm typing it in the chat box. And remember, you're welcome to send any questions or comments to my email. And one more resource that I would like to share with you is our YouTube channel, which is YouTube Frontline Solvers, and I'm going to share the link here in chat box. And here we post demo videos, more advanced short videos on each of the features, and we look forward to future webinars with you. We appreciate your time, and I'm going to end the webinar. Bye for now.